Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, thanks very much, Rob. Can you all hear me? The microphone's working? Great. Welcome to Cambridge. Welcome to MSR Cambridge. I thought what I'm going to do for you is give you a general overview of Microsoft Research, Cambridge, let you know, who we are, what we do, and then give you an example of a few projects across the lab before I turn it over to my colleague, Chris. So Rob showed you a nice picture of our shiny new building. If you want to get an idea of where that is, it's in the middle of the world, of course. It's in Cambridge. So this slide shows you the entirety of the Microsoft Research organization. So there are 7 sort of core labs. And the first lab was in Redmond, where the headquarters are, of course. Cambridge was the first lab outside of Redmond and the first lab outside of the U.S. And we've been here for 16 years now. So it's a sort of venerable institution, Microsoft Research. The lab in Redmond was founded in 1991. So it's we've been around a long time. Soon after we were founded, there were labs set up in Beijing and Bangalore, and then more recently labs in other parts of the U.S., most notably in the other Cambridge, which they had to call themselves MSR New England because we were MSR Cambridge. And there's a small outpost in New York that was part of the Yahoo acquisition, and there's a small lab in Silicon Valley as well. And then we also have 3 advanced technology labs, which are sort of halfway between a product organization and the basic research lab that MSR represents, which you'll hear more about. And then in Redmond, there are also a few allied organizations to MSR that are kind of like the ATLs, the Extreme Computing Group, Fuse Labs, and Station Q. Station Q is our group that is looking at quantum computing, so which is about sort of as far out as you'll get there. It gives you an idea of the scope of the activities that we undertake in MSR. So, as I said, MSR has been around since 1991. We have had the same mission statement for all of that time, and it's a 3-part mission statement. Our number one goal in MSR is to advance the state of the art in computer science. And that's computer science taken very generally. So in fact, these days, that includes a wide range of fields sort of outside of computer science, but on which computer science has an impact or which has an impact on computer science. So we also have psychologists and sociologists and biologists and ecologists, as well as computer scientists. So that's a very general, that's computer science at its most general. But the advancing the state of the art is in the sense of in the same way that academics advance the state of the art. So it is important to understand that MSR at its core is an academic institution. We measure our people largely on their academic output, on their quality, peer-reviewed publications in top journals and conferences, just as if we were academics. Now, if that was the entirety of the story, you'd probably be wondering, well, why is Microsoft paying for this? We do have 2 other parts of our mission statement, the second of which is to transfer technology into Microsoft businesses. But it's kind of, secondary is the wrong word, but it is a second goal. Our number one goal is that advancing the state of the art in this academic fashion. But as sort of equal but second goal is to transfer ideas that we come up with into Microsoft businesses. And we do that all the time. And in fact, one of the journalists that I spoke to yesterday said he wanted to know what fraction of the projects that we do in MSR make it into Microsoft products. And I thought for a moment, well, that's not the really interesting number. The other number is interesting, and virtually every product that Microsoft sells has had some impact from Microsoft Research. And I think that's the more important answer there. And so, and as well as that sort of mainline transfer of ideas into the business, a couple of examples of which I'll give you, we also have 1 or 2 other ways that we can transfer technology, and I'll come to those later. The third part of a mission is one that we talk about leadership, leading Microsoft into the future. And this is really the idea that a basic research lab like ours that has this freedom to do sort of research into anything that we want to, has an obligation to look further forward than the Microsoft business groups can do, to see, well, what's coming next? What should we be gaining expertise in, so that when this new thing comes, when there comes a time when those new things can be taken to market, that we're ready to do so. So that's the third part of our mission, these sort of eyes into the future. And so overall, that makes this a very interesting place to work. This is, if you're somebody who otherwise would have been an academic in one of the fields that we do research in, this is a great place to work, because if you walk around here, it will feel like a university department. People are hired because they're good at what they do, not because we want them to fit into a certain area. We hire them and we let them do what they want to do. We let them research the areas that they want to research, and we just sort of assume that good things will happen from that, and generally they do. So that's the sort of culture of the place. It's very open. Another good example of this is that there's no formal process anybody here has to go through to publish a paper. They have an idea, they work with their collaborators inside and outside, and they choose to publish the paper. Now, of course, the people are generally sensible, and they'll probably talk to our patent lawyers and patent a few things before they publish if they think this is going to be valuable to the company. But that's up to them. There's no formal process that sort of obligates them to do that. And again, that just fits with this idea of having the ideas bubble from the bottom up. I think something that we often say here is that Google was famous for saying that you had your sort of 20% time when you could do anything you want. And when we're interviewing candidates and we're trying to say, no, you don't want to go to Google, you want to come to MSR, we say, because 5 days a week, 100% of your time, you can do what you want to do, which is true. Just take a drink here. So this slide is the research areas that cover what goes on in this lab. So this is are the 5 major areas that Cambridge covers. I'm not going to talk about these in any great detail because you'll be hearing from people sort of across these areas later in the day. I guess the thing to see is that there's a very wide range of stuff, from sort of core computer science like programming principles to more a wider range in things like network economics, human-computer interaction that includes sociology, biology, and ecology, as I said. So there's a very wide range of stuff we do. And again, it isn't like somebody said, Cambridge, you shall do these 5 areas. These have just grown up over the years because of the people that we've hired. And as happens in academic departments, the hiring process, you gradually sort of accrete areas of expertise, and that's what's happened here. But it wasn't any sort of top-down process. And which also means that you saw that there are many other Microsoft research labs. We often do have groups doing similar things sort of across the labs, and that works out okay. We collaborate a lot of the time where it makes sense. Occasionally you get a bit of healthy competition, which is good too. So there's really no sort of orchestration. The reason that these 3 sort of product group logos are across the bottom there is something that we've done more of in the last couple of years is we've had what we call embedded product groups with us. And all that really means is people from various Microsoft product groups living with us in this building. And that has proven to be a very good thing for them and for us, because it means that they have sort of immediate access to ideas from MSR, which they can take back to their sort of management and say, look, this is something cool I think we should be using. And it also means for us, being 5,000 miles away from the sort of, the kind of heartbeat of Redmond, it gives us a sort of easier access to getting our ideas in there as well. So it's a two-way street, and that has worked very well. And I guess on top of that, with some recent acquisitions, we acquired Skype a couple of years ago, and they're mainly in London, so that's very advantageous for us, especially with our new location. And another point is that we pay a lot of attention to the pipeline of people that we might hire. And this actually goes all the way down to education. So we have a very, we engage very strongly with academia. I said that we behave like academics, but we also work with academics extensively. So our researchers, very, very commonly work with academics from universities all over Europe and all over the world, really. But we also have a couple of formal programs, one of which is our PhD program. So we fund about 100 PhD students at any one time over their sort of 3 or 4 years of their PhD. And we do this by targeting supervisors, so academics that we know are good, and they apply with a project in mind. And if they get one of these fellowships, then they then identify a student. But key to this is that we tend now only to grant these where there is somebody in this building who is going to be co-supervising that PhD. So it gives us this very tight engagement with young, vibrant PhD students and their ideas, but also it lets us identify early people we think that we should maybe get as interns, then postdocs, and then hire them. So we have a very, people are our most important asset. So the way that we recruit them is important, and that starts with our academic engagement even at the PhD funding level. Right. A little change of pace here now. So I'm now moving on to the sort of second and possibly third part of our mission statements. And a couple of the example projects that I'll show you later will give you an example of the more, what I would call the typical tech transfer that we do. Because most of what we do when we do technology transfer is we take ideas that we have and we get them into Microsoft products. And there's lots of examples of that. But occasionally, we do something that isn't either ready for a Microsoft product or just doesn't fit our product offerings at the time. And in that case, we're able to license things out to other things. And that's what happened here. I'll just give you a little bit of background on this. So, and this also goes to show how the long-term aspect of MSR is an important thing. Because this thing, which I'm wearing one of, which is called Autographer, goes back to a project we had here that was called SenseCam. And that started in 2004, I think. So this is a long time ago. And it was really one of these sort of curiosity-driven things where one of our researchers was building a sort of what she called a black box for human beings. It was just a box that had a bunch of sensors on it, accelerometers and light sensors and temperature sensors. And the idea there was to just monitor the environment that you're in all the time. And then if you were in an accident or something, you could see how fast you were moving, and where you were, and sort of what was happening to you at the time. And then she just had the idea, I wonder what would happen if I bolted a camera onto this thing. So she did. And she used the sensors to trigger when the thing takes pictures. So the idea here was that, so there's all these sensors on board. And so if you move suddenly, it would take a picture. If the temperature changes, so maybe you've gone from inside to outside, it takes a picture. If the light level changes suddenly, it takes a picture. If somebody walks in front of you, it takes a picture, and so on. So it tries to take pictures at these interesting times. And then another sort of happenstance thing is that the head of the neuropsychology department at Addenbrooke's Hospital here in Cambridge saw this thing and thought that would be a good memory aid for my memory-impaired patients. And so that started a whole seam of work. And I'm not going to talk about that in detail because you may have seen this before if you've monitored anything we do. But that led to a whole seam of research around the world, not just here, but neurologists and neuropsychologists and biologists around the world were looking at why the types of images that this camera took had such a profound effect on people's memory. So it actually, we ran with Addenbrooke's formal clinical trials of early Alzheimer's patients, people that had lost their memory due to strokes, and reviewing the images that came out of this camera just had a profound therapeutic effect on their memory. And there's still ongoing research in this area. I just had an email from a PhD student at Oxford who's done a PhD using SenseCam for this purpose and has just had his Viva. But so all that is to say that this was this ongoing research. And at the same time, we also, while all this sort of medical research was going on, we noticed that this was just fun. The sort of image sequences that this thing took were fun to kind of replay with your family. And so we initially went to the Microsoft hardware guys and said, look, this is a cool idea. Do you want to build this? And we had a long sort of exchange with them. And it just turned out that at the time, this didn't fit their sort of roadmap. So they decided not to build it, which gave me leeway to try and license it, which I did. And so I licensed it first to this company OMG in Oxford. We licensed it to them just for use in the medical domain, and they built them and sold them for that. And then they came back to us and said, we would really like to build this for a general consumer launch. And they set up a little separate company called OMG Life that has launched this now under the brand name Autographer. They completely sort of redid it. I'm wearing one now. And they just launched it this year. So you can actually buy these things now. And so I think that, that's an interesting sort of path from a very sort of serendipitous research project to a shipping product. And it's a technology transfer that is not the usual type of one, but is something that we do every now and again. So just a little sort of a story there. Also a little pitch for the Autographer guys. So now I thought I would turn to a couple of research projects that have gone on over the lab, and also another tech transfer story or two. Under the general guise of how is the way that we interact with computers changing? And I think you'll all agree that it is, and how might it change further in the future? So here is an obvious example. Is that going to play? Do I have to click it to play? There we go. This is just a short video, but most of you have probably seen this. I'm not sure how long this is. I won't dwell on that because you've all probably seen this. So Microsoft Kinect, a new way of interacting with your gaming console and without having to use any sort of a controller. You've seen that. Now I want to also tell a little tech transfer story about this because the success of Kinect has been a really positive thing for this lab. We had a lot to do with this. And the tech transfer story here is again a slightly different one than normal. Is that the product group came to us. So the Xbox guys were kind of building this themselves and doing a very good job of it. And they just ran into a roadblock of not being able to make the skeletal tracking run in real time. And they knew that the Cambridge lab, and actually I think the Asia lab as well, both had strong computer vision groups. And they came to us and they said, can you help us with this? And so we sent our guys away for 6 months, and they did. So which has led to the product that you saw. And the real sort of guts of this is an area called machine learning, which Chris is going to tell you a lot more about after my talk. Chris is a world expert in this area. But the sort of essence of what that means is learning by example. And so this shows you this is a number of different body poses with the different parts of the body labeled in different colors. And you can see that there's lots and lots and lots of these, because if you want to do machine learning, you need lots and lots of examples to learn from. And interestingly here, and I think Chris can probably tell me this, but I think one of the innovations here is that these were synthetically generated examples. So we didn't get people to dance and hold their arms up in all these different positions. We generated those synthetically and used those to train the classifier, which then was able to work out which way that you were standing. So you can see here, this is just a very quick outline of how it works. And I guess the key is the sort of hardware innovation was an inexpensive depth camera, which is a sort of camera which gives you information as to how far every pixel in the image is from the camera. So that's what that first image is. The darker the pixel, the closer it is to the camera. And taking that information, you can then infer which part of the body each pixel is sort of assigned to, and then you can use that information to further sort of postulate where the joints are and what they're doing. And this is the so-called skeletal tracking. And again, Chris may tell you more about that. But the real key here too, and one of the things that I think we contributed was this no tracking or smoothing. This is all done frame by frame. There's no frame-to-frame information being used, and that's important to make the thing sort of work consistently in a way that consumers will accept. Because if you use tracking and the tracking goes wrong, it'll go badly wrong. And so we had to make it work this well with no tracking. And that's one of the things that we did. But there's more to be done. So if you've used this, or if you have read about it, you'll know that we can track the human skeleton very well, and that includes your hands. We know where your hands are, but we don't really know what your hands are doing. And there will be more interesting things we could do if we knew what your hands were doing. And so that's a problem that we're looking at now. So we're doing more of that kind of data collection of hand poses, and we're training our classifiers on that data so that we can have more information about what your hands are doing and not just where they are. And that's work that's going on largely in this lab, also in other labs, I think. And this has led us to look at other applications. Because if we can tell what your hands are doing, then maybe we can use it not just in front of the games console, but in front of your PC. And this is a research project that's going on here that Abby will tell you a lot more about later on. But you can see that my colleague Chris here, is interacting with his PC using the mouse and keyboard like normal, but he's also able to use his hands to do various kinds of gestures. I don't know whether we missed the search gesture, but you see he's just sort of swiping on the outskirts of the keyboard to do those sort of swipe-in type moves. I think he'll do a search gesture here in a moment. Well, there's a sort of narrative to this video that I've turned off, but the idea here is that we identify regions above the keyboard, on the keyboard, and around the keyboard where we can sense where your hands are and what they're doing using the technology that I just mentioned. We can use that to implement various types of gestures that you can use. And the key here, and as Abby will make clear later, these are gestures that are used alongside the mouse and keyboard, not instead of. So you may have seen the leap motion controller, and that's much more of a kind of minority report sort of thing, where most of what you're doing is in the air. And that's not such a good idea. And that gets to my next slide, is that a lot of the work on this project has gone into thinking carefully about, if we can tell what your hands are doing, what gestures should we look for that we could use in anger in real work over a long period of time. And there's a number of design principles that Abby will go into later that we try to adhere to make these low effort and ergonomic, and ones that you really could use and use in conjunction with the input modalities that you already have. And these are a few of the gestures that we have. One of them that you'll see later, and I think probably the most compelling one, is this one that we call the peek gesture, which is turning your hand over like that to look at the document that you were just previously working with. And the idea there is that as you're typing, it's very natural and easy to just flip your hand over, look at that previous document, flip it back, and go back to your typing, and that sends it away. And you'll see that later. But that's one example of these sort of integrated ergonomic gestures that this project looks at. I won't tell you any more about that because Abby is going to. I'm going to move on to something else now. This, in the spirit of One Microsoft, I'm going to show you another idea about how interaction in the future might work that came from one of our other labs. This is from a guy called Andy Wilson in MSR Redmond and his group. Let me just play this quick video for you, and then I'll explain to you what it does. It's called Illumaroom.
Xbox, go big.
Turn on those lights, maybe. Watch for something now, yeah. That little bit at the end, I think, is the coolest thing. I sat in this room at. We have this annual sort of research trade fair that we call TechFest, and I saw this there, and it's really amazing. And what he's done here is he's used a camera, or a depth camera, in fact, and a projector to as you saw, to basically expand the field of what you're interacting with to be your entire room. There's a lot of clever stuff going on to make the sort of mapping onto the furniture in your room be as well done as it was, and that's because the depth camera scans the whole room, gets a 3D model of the room, and can sort of adapt the way that the images are shown so that it fits onto your furniture. But you saw all sorts of effects, like I think when he shot a gun or something, the whole room kind of vibrated, and it's just an amazing effect. And I think the thing is, this, in terms of where interaction is going, it's these two sides of things. It's new input modes, like gesture, as we saw, and Abby's going to talk later about other ones, because gaze and voice and even brain interfaces, these are all coming, and these are things that we're looking at, at how we would use them when they are commercially viable. But then there's also the output side of things. Large displays are getting a lot cheaper, and other technologies like this are going to make it possible for almost every surface that we see to be part of your computer's display. And I think this is an example of what that might lead to. How am I doing for time, Rob? 5 minutes. Okay. Well, that's give me time to quickly tell you, kind of change scenes. So that was all about user interaction. I've kind of hinted at some things to come, and you'll see some more of that later in the day. I thought I would just give you a quick flavor about some of the other research that goes on in the lab, because it's actually, my group does a lot of the user interaction stuff. So I don't want to be seen to be biased that way, and we have a lot of other cool stuff going on as well. So this project is one from our systems and networking group. which I suppose was arguably the first group. I guess MLP and sort of SNM were the sort of early groups. But here, the idea is to make cloud performance predictable. And we can already do that with CPU. So you can get a dedicated VM from a cloud provider like Azure. But the problem is that network traffic and storage bandwidth are also key to how fast your job is going to finish. And at the moment, we have no way to guarantee performance levels on those two fronts. And so this is what the systems guys were looking at. So the idea here is that if I have my own sort of enterprise server set up, and I have a MapReduce job, or John has a MapReduce job, he wants to run it, he knows exactly what he can offer in terms of network bandwidth and storage bandwidth and CPU time. So he knows that that'll take 4 hours on his enterprise system. If he says, I don't want my own system anymore, I want to run this in the cloud, all of a sudden he doesn't get those same kind of guarantees, because cloud is all about time on VMs. So you have the sort of CPU time that you know about, but you don't know what's going to happen with the network traffic or the storage traffic, and so the time it may take longer than the 4 hours it would take in the ideal situation when it's your own network. And that will also vary the cost, because you get charged kind of by the hour on most of these kind of systems. And so they were thinking, well, what can we do about that? And so what the idea here is to have a sort of two-sided thing, to allow tenants to say what their constraints are. Say, I want this job to finish in 3 hours, and I want it to cost less than $400. And it also lets the providers work out how much it will take for how many VMs and what network bandwidth and what storage bandwidth they'll need in order to finish the job in less than 3 hours. And then they can decide whether that's worth $400 or not. And really the sort of innovation here, and I won't go into the details, A, because I don't really know them, and B, because it would take too long, that they have come up with ways of working those things out. And it's important to say, too, that this, in general, for general computational problems, is essentially an impossible problem. It's one of these NP hard problems. But they have worked out a way that enables this to be done for MapReduce-like applications, which covers a wide range of things that people need to do in the cloud. So that's very interesting work, and that's so that is enabling this job-centric pricing, where you can say, I will do this job in 3 hours for $300, and I guarantee that it will be finished. And lastly, I'm going to move on to some work that's been done in another of our groups, our computational science group. And this is the group that has the biologists and ecologists as well. And you're going to hear from Lucas later, I think, from that group, talking about some of this work. This is work that Lucas is not going to talk about, which is done by some of our computational biologists. And what this is the only slide I have, and I don't expect you to really understand it, but this is a tool for biologists to reason about biological systems like cells. What's interesting here, what's actually really interesting here, is that this actually crosses 3 of our groups in the lab. Because what they have done here is they have taken the formal mathematical methods that our programming principles group uses to analyze computer programs, and they've applied that to biological systems. So they can prove things like the stability of the chemical pathways in a cell corresponding to whether a piece of software will do what it's been specified to do or not. They use those same techniques for that. And then some of the social scientists in my group have gone to see how biologists actually behave when they're doing this work, and have tried to build this tool to mirror the way that biologists work. So we've taken mathematical techniques from computer science to model biological systems, and sort of ethnographically derived practicing biologist practices, and merge those into this tool that is now being used by biologists to do cell biology. So I think that's my last slide, and I think with that I'm going to turn it over to my colleague Chris, who's going to give you some more details about dealing with uncertainty. Thank you very much.